Right.
7 St. Augustine.
Back on quarter.
How long drive is that?
Was it? What's the speed? Oh, speed. More importantly.
All right, good afternoon. Welcome again to math. And we are on lecture 29. No, 19.
Yeah.
Yeah.
I missed a lot.
10 lectures in the last 2 days. Yeah, talking about that, I with this change of blocks from 60 minutes to 50 minutes, there's a lot of things I'm gonna have to cut from this last portion of the semester. So I'm not gonna try to go fast. I'm just going to maybe skip one of the methods, maybe just talk about it, and then just make sure I don't include it in the homework assignments or the exam. All right. So we were discussing separation of variables for partial differential equations. Again, this is lecture number 19. And we had started with the following problem. I'm not going to recast the whole thing. So given the governing equation, Laplace of t of x and y is equal to 0 with boundary conditions t at 0, comma y is equal to 0, t at L, comma y is equal to some function, some given function of y. So that's the left edge, the right edge. The bottom edge would be x, comma 0. That's also equal to 0. And the top edge is also equal to 0. All right, so we have this problem in hand. It's a partial differential equation because the function that we're seeking, the temperature as a function of x and y, is a function of two variables, and therefore this differential equation contains partial derivatives. All right? So we know that separation of variables applies because the problem is linear, because the problem is framed in an orthogonal coordinate system. It is in a rectangle. Okay? We know that it applies because there's only one non-homogeneity between governing equation and boundary conditions. And initial condition, there's no initial condition because there's no time involved in here, in this problem. So therefore, SOB applies. SOB applies. And what we had said was that let's assume let the temperature of x and y be equal to some function x of x times some function y of y, and after some implementation, kind of find out what the first derivative of t, partial derivative, second derivative, or so, these differential equation became x double prime of x divided by x is equal to minus y double prime of y divided by y. Okay, so we got to that point. We'll repeat this process for the next few examples, but that's, in summary, what we did over the last 20 minutes of the last lecture. All right, so what did we gain? First of all, we arbitrarily said that we're going to let the temperature, which is a function of x and y, be the product of two functions of a single variable. And somehow, we turned the original partial differential equation, which has partial derivatives in x and partial derivatives in y, that's what the Laplace operator is, into this equality, which has ordinary derivatives, or total derivatives, right? That's what we mean by x, what we imply by x double prime is just the total second derivative of x with respect to x squared, and this one is the total of y with respect to y squared. Okay, so we need to now determine x and y somehow. So we went from trying to determine one function of two variables to trying to determine two functions of one variable each. Okay, so at this point is when we need to rationalize and identify the fact that, see, if we arbitrarily said that this function t of x and y was going to be a function of x times a function of y, and we managed to turn the differential equation, because the differential equation is linear, we managed to turn it into separated terms of x on the left and separated terms of y on the right. See, the function x is a function of x only, and therefore its second derivative is only a function of x only. And the function of y, and the function y is only a function of y, therefore its second derivative is also only a function of y. So these, on the left hand side, is only a function of x, and right hand side is only a function of y. Now, is that even possible? Can we have a function of x be equal to a function of y? No. Somehow, the x dependency has to cancel out on the left, and the y dependency has to cancel out on the right. So whatever function x is, when we take its second derivative, the x dependency has to cancel out, and the only possible way that these can be equal to this is if both are equal to a constant. So the only possible way that left-hand side is equal to right-hand side is that both are equal to a constant. Now, this is a key step in separation of variables. And I'm sure it took a couple hundred years for somebody to realize this. Okay? Now, is that clear? That what we're saying here? The function, whatever's on the left-hand side cannot be a function of x, because whatever's on the right-hand side is a function of y, and this equality has to hold, and therefore, whatever's on the right and on the left needs to be equal to a constant. So what we're going to do is we're going to say x double prime of x divided by x of x is equal to minus y double prime of y divided by y of y, and we're going to set that both equal to a constant. And that constant we're going to call lambda squared. And we are going to decide whether that constant is positive or negative based on only one criterion. Okay? We make it square to make sure it's a positive number. And then we're going to assign a sign to it, a plus or a minus. Okay? Now, the sign of lambda squared will be selected based on the direction on which we want eigenvalue problem. Okay, now let's see what that means. This problem has two directions, direction x and direction y. Again, I'm going to draw it. Basically, this is x, this is y, and this is a rectangle in which we are trying to solve the equation Laplace of t of x and y is equal to 0. This goes from 0 to L, and this goes from 0 to small l. The boundary condition here is t equals 0. On this wall we have t equals 0. On this wall we have t equals 0. And on this wall we have t equals to some known function of y, which can be a constant, and that really doesn't matter. It's just some prescribed non-homogeneous condition. That's the only thing driving that problem. If that condition on the right-hand side were to be also 0, there is no possible way for the solution to be non-trivial. Okay? If this was a 0, nothing is driving this problem. The solution is 0, period. Okay? So the only thing driving this problem, the opening equation is homogeneous. There is no generation here. There's no energy generation internally. All these equations, all these conditions are 0. The only way taking this out of equilibrium is the right hand side force non-homogeneous condition. Okay? And it can be, I'm just generalizing it as f of y. It can be a constant, it can be whatever number. Okay? So now we have one homogeneous direction, that's the y direction, and one non-homogeneous direction, that's the x direction. See? So this direction here x non-homogeneous. And this direction here, y homogeneous. The problem in y, we'll see its two boundary conditions of y equals 0 and how y equals small l be equal to 0. Therefore, we must form or construct an eigenvalue problem in the y direction. So we must select that sign up here so that the resulting problem in the y direction is an eigenvalue problem. Alright? So I'm going to pick the plus sign. And the consequence of that is going to be obvious. Y is a positive sign, is the right choice. So the right choice is the plus sign. So therefore, x double prime of x divided by x of x, which is equal to minus y double prime of y over y of y, is equal to plus lambda squared. I am going to decide that that constant that I use to identify the equality is positive. Because then, if you notice, this is going to result in two problems. X double prime of x minus lambda square x of x is equal to 0. And y double prime of y plus lambda square times y of y is equal to 0. Okay, disregard this little mark here, that's nothing. By picking the plus sign, then this becomes two ordinary differential equations. So this right here, we know is an eigenvalue problem. ODE. And this is a non-eigenvalue problem. ODE. Why? Well, because the solution of the top equation is cosine hyperbolic, sine hyperbolic, and those don't oscillate. The solution of the bottom equation is sines and cosines. Those oscillate. For a problem to be an eigenvalue problem, the solution needs to oscillate around the x-axis or around the independent axis. Alright? Is that clear? This is the whole key about separation of variables. Selecting the right sign and forming two problems out of a single one. Now, if this problem were three-dimensional, we'll be forming 4 problems. If this problem were 3 dimensions plus time, we'll be forming 4 different problems. But it's just a copy of what we just did. Okay? All right, let's solve the y problem first. So we have these. Y double prime of y plus lambda square y of y is equal to 0. Remember what the solution is? It's A cosine of lambda y plus B sine of lambda y. Because of that positive sign, the roots are imaginary, and therefore we end up with cosines and sines. This is a general solution y of y. Okay. But we still have constants of integration. And we need to see if we can figure them out. Alright? So, to arrive at particular solution, we need BCs, boundary conditions. Alright? So let's look at the original boundary conditions, right here. We're solving the y problem, which is this one. When y equals 0, the temperatures equal 0. When y is equal small l, temperatures equal 0. Alright? So those are the boundary conditions that we have. T of x comma 0 is equal to 0. And T of x comma L is equal to 0. Those are the boundary conditions in the y direction. This one and this one. And the two of them are homogeneous. That's precisely why we selected the plus sign, and that's precisely why this resulted in an eigenvalue problem. Now, those are the boundary conditions for T, not for Y. We need boundary conditions for Y to be able to determine A and B. But we already said that T was equal to x of x and y of y, which is 0. And this is x of x times y of L, which is 0. Right? So we haven't assumed anything else, anything new. We went back to the original assumption that T was the product of two functions, x and y. And therefore these needs to be these. Alright. Now, we have a product of two functions equal to 0. So either x of x is equal to 0 or y of 0 is equal to 0. Where are we going to select? We have to select y of 0 is equal to 0. And we have to select y of L is equal to 0. Why is it that we cannot select x of x equals 0? Why not the other choice? For these product to be 0, either this one or this one must be 0. If we select x of x equals 0, what happens?
We don't have any boundary condition.
What's that?
We don't have any boundary condition.
Well, no, if we select x of x equals 0, then if x of x is equal to 0, the temperature is 0, so we arrive at a trivial solution. That doesn't work. Okay? We're looking for a non-trivial solution to this problem. We cannot select x of x equals 0 because it leads to a trivial solution. That is, t of x and y is equal to x of x times y of y, and if this one is 0, then the solution t is equal to 0. That's called trivial. So we have these two conditions. So let's start with the first one. Y of 0 is equal to 0, which is equal to a cosine of 0 plus b sine of 0. The cosine of 0 is equal to 1, the sine of 0 is equal to 0, and what do we conclude out of this? That a is equal to 0. So we determined already one constant of integration. Now y of L is equal to 0. That's equal to, well, we know that a is equal to 0. That is only b times the sine of lambda L. Well, again, we're presented with the same situation where we have the product of two terms is equal to 0. We cannot select b equals 0 because that will lead to the whole function y being equal to 0. That's a trivial solution. So the only choice is that the sine of lambda L is equal to 0, and that would lead to lambda n equals to n pi over L. right? Those are the eigenvalues. For any value of n, integer value of n, this is true. So those are the characteristic values that make possible that y of y equal to b sine of lambda n y eigenfunctions. This portion here, eigenfunctions. So those are signs of different frequencies. There are obviously non-zeros, but there are zero at the ends. A y equals 0 and a y equal L, there will be 0 because this coefficient lambda n produces that characteristic. We still have that constant of integration b. We'll worry about it later. Okay, but this is as far as we can get with a y problem. Let's see what we can do with the x problem. So the x problem, we have x double prime of x minus lambda square x of x is equal to 0. All right, and what is the general solution of this? X of x is equal to c times the cosine hyperbolic of lambda x plus d times the sine hyperbolic of lambda x. This is definitely not an eigenvalue problem because it leads to functions that do not oscillate. The hyperbolic functions do not oscillate. And this is a general solution, x of x. Okay, now again we need BCs, boundary conditions. And in the x direction, we have these two boundary conditions. When x equals 0 and when x equals capital L, these are the two given boundary conditions. You can see here in the schematics. On the left side wall of the rectangle, we have temperature equals 0. And on the right hand side wall of the rectangle, we're given that temperature is equal to some function of y. So, what's given is that t of 0 comma y, that's on the left hand side, is equal to 0, and t at L comma y is equal to 0. We can decompose that into x of 0 times y of y is equal to 0. I'm sorry, this is f of y. And we can decompose this one into x of L times y of y equals to some function f of y. Alright, so again we're presented with this choice. Either x of 0 is equal to 0 or y of y is equal to 0. That's easy. We need to say that x of 0 is equal to 0. We cannot take y of y equals 0 because that will lead ultimately to a trivial solution. We don't want that. Okay? Now how about the one on the bottom? We have a product of two terms. X of L, which is just a number, times y of y is equal to f of y. That one cannot be separated. We cannot say anything about either of the two. So this one cannot be separated. Cannot be separated. So basically we are going to reserve the non-homogeneous BC for later. We cannot do anything about it yet. So what we have, the only thing we have is that x of 0 is equal to 0. And therefore, that's equal to c times the cosine hyperbolic of 0 plus d times the sine hyperbolic of 0. The cosine hyperbolic of 0 is equal to 1, the sine hyperbolic of 0 is equal to 0. Which means that c is equal to 0. So the only thing that we're left with is that x of x is equal to d times the sine hyperbolic of lambda x. Now we also know already that lambda is an eigenvalue, and lambda has an index associated with it. So lambda can take multiple values. All right, now we're ready to merge the two solutions. Now we're left with two constants of integration. See? One is b here on the y solution, and the other one is d here on the x solution. But recall that when you merging the two solutions, t of x and y is equal to x of x times y of y. Then you're going to multiply this one times this one, and when you multiply constant b times constant d, we can just call that constant e. That will be the sine hyperbolic of lambda n x times the sine of lambda n y. Such that lambda n is equal to n pi over L, and n are all the numbers from 0 to infinity, all the integers from 0 to infinity. Make that possible. All right. So we have a ton of possible solutions here. We have infinite, basically, number of solutions. Not only because we have that constant of integration e, that makes these a family of solutions. So any constant of integration here that we plug in will satisfy the governing equation and the three conditions that we've used so far. Okay? So we've satisfied the governing equation. This will satisfy the Laplace of t equals 0. Okay, that's where we started. And it will satisfy the three homogeneous conditions that we've already employed. We still haven't used the non-homogeneous condition. Okay, we couldn't yet. So, but not only because we have that constant of integration, we have infinite possible solutions. For every value of lambda, this is true. For every value of lambda like this is true. So all of these are possible solutions. One oscillate at different frequencies than the other. Okay? So we have a ton of possible solutions, each of which is just a waveform that oscillates at a different frequency. That's what the sine is. The larger this number is, the faster these oscillates. This one, I'm sorry, oscillates. This one doesn't oscillate. Okay? That's what it is. Superposition of waves. And when Fourier came up with this technique to solve heat transfer problem, they told me it was crazy. They wouldn't even give him a job. He applied to his school for faculty position, and they told him that he didn't have enough rigor in his methodology, because how is it possible that you can solve a diffusion problem, which a heat transfer problem is a diffusion problem, which we know is something that decays and equilibrates. How can you suggest that it can be solved with waves at different frequencies? And he said, well, the math is there. If you put them all together, they become a flat function. They become a diffusive function. Is that even possible? That we take all these signs, right? And well, the first sign when n is equal to 1, when n is equal to 0, don't even worry about it, because when n is equal to 0, the sine of 0 is equal to 0. So that solution is just trivial, okay? But when n is equal to 1, you have a single wave. Well, in the y direction, you have a single wave. When n is equal to 2, you have two waves. When n is equal to 3, you have three waves, okay? And he said, well, when we superimpose an infinite number of these, we get the function we're looking for. And that function doesn't have any oscillations. He said, well, that's not possible. If you have oscillation over oscillation over oscillation, you're going to see waves. Well, it turns out that if you add up all of these up until infinity, that oscillation will disappear. And back then, in Fourier's days, they didn't have a computer to add up an infinite number or a semi-infinite number of functions, but he did it by hand anyways, and he thought he was cheating. So, anyways, he ended up getting a position and became Fourier. So that's only possible because, remember, we're solving a linear equation. And I don't know if you remember when we started talking about differential equations, linear equations satisfy the superposition condition. That if you have one solution to an equation, and you have a second solution to the same equation, the linear combination of the two would also be a solution to the same equation. So, if we apply that principle, using the superposition principle, which says basically two solutions of the same linear ODE can be linearly combined to produce a third solution. So that means that we can suggest that t of x and y will be the summation from n equal 1 to infinity. Notice that I'm not including the 0 because we know that sine of 0 is equal to 0. Okay? Of e sub n sine hyperbolic of lambda n x times sine of lambda n y. And this is all written in this little book written in French. I have a first edition of that said that the theory of heat by Fourier. That's a temperature. But that's still a general solution. General solution with an infinite number of constants of integration E1, E2, E3, all the way to E infinity to determine. We need to somehow determine an infinite. Is that even possible? We know how to find one, but can we find an infinite number of them in one shot? Well, that's where we're going to use another one of these techniques and another one of these principles. That is going to come in very handy because we only have one condition left that we haven't used. And somehow, with that single condition, we need to determine an infinite number of coefficients or constants of integration. All right, so the only BC that we are yet to use is the temperature at x equal L and y is equal to some function y, okay? Where that function y is given. All right, so let's try it. Let's see if using that we can somehow determine En. So therefore, f of y is equal to the summation from n equal 1 to infinity of e sub n sine hyperbolic of lambda n big L times the sine hyperbolic, the sine of lambda n y. Doesn't seem trivial. Even if I tell you that f of y is equal to 1, just a number, it would be difficult to figure out a way, an obvious way of determining all these constants E. So, what we're gonna do is multiply both sides of this equality by the eigenfunction sine of lambda m y. And I'm going to use a different index because I cannot use the same index and plug it inside the summation. So this is going to be f of y times the sine of lambda m y is equal to the summation from n equal 1 to infinity, en sine hyperbolic of lambda n l sine of lambda n y times the sine of lambda m y. And now we haven't done anything wrong. I'm just multiplying both sides of that expression by a known function. I know exactly what that function is. It's the sine of m pi over small l times y. I just elected to multiply both sides by it. Now integrate over the y domain, and that is from 0 to L. So if I integrate the left from 0 to L of f of y sine of lambda m y dy is equal to, and I'm going to kind of skip a step here and push that integral all the way inside because none of these depend on y. But these do. All right. So what do we see there on that integral on the right-hand side? It's the integral of the eigenfunction times itself evaluated at a different index. And what do we know? From the orthogonality property, the integral from 0 to L of the sine of lambda n y times the sine of lambda m y dy is equal to either 0 if n is different than m, or remember L over 2 if n is equal to m. We already solved that integral in particular and showed that that was the case. These eigenfunctions of the property of being orthogonal to each other with respect to a weight function, and in the case of this equation that we solved, the weight function is 1. So this integral here on the right hand side will vanish for every value of n except when n is equal to m. So let's write that. The integral on the right hand side will vanish for every value of n except when n is equal to m. Right? So we expand the summation from n equal 1, n equal 2, n equal 3, all the way to infinity, and out of all those infinite terms on that summation, only one is non-zero. Right? So basically, what happens is that the left-hand side stays the left-hand side, and the right-hand side, well, all the terms in the summation go away except the m term, sine hyperbolic of lambda m l times the integral from 0 to L times the sine square of lambda m y dy. Is that clear? all the terms in the summation disappear because of this orthogonality property, except this one, when n is equal to m, and we know that this integral is L over 2. Well, the integral of all trigonometric eigenfunctions is not necessarily L over 2. We already proved it for the sine. The cosine is also L over 2, but some other ones might not necessarily be L over 2. Okay. So great. So I have EM is equal to 2 over L times the sine hyperbolic of lambda m big L times the integral from 0 to L of f of y sine of lambda my dy. And that's it. We may switch back to n and say that E sub n, which is what we're looking for, is equal to 2L sine hyperbolic of lambda nL times the integral from 0 to L of f of y sine of lambda ny dy. And along with the temperature of x and y being equal to the summation from n equal 1 to infinity of E sub n sine hyperbolic of lambda n x sine of lambda n y such that lambda n is equal to n pi over small l. This is the particular solution. Whatever that function f of y is given. It's a known function. So now the solution is known. This is it. And somehow all these waves of different frequencies will cancel out and produce a solution that will satisfy these equations and this equation and these boundary conditions for all values of x and y within that rectangle. And it will be diffusive. It will be an equilibrium condition where the temperature on the borders will be 0, the temperature on the right edge will be whatever this function is, and inside it will be the diffusion of that within the domain. That's what heat transfer is, heat conduction in this case. Okay? The solution in the interior cannot be any greater than f of y or any smaller than 0. It's an equilibrium between all these, driven by the boundary conditions. There's no generation in the governing equation. Okay? And somehow that is possible through waves. You can put it on the computer and verify it. So for instance, for example, if f of y, the given function, let's say, is equal to 1, I am told that the temperature on the left, the temperature on the bottom and on the top is 0, and on the right is equal to 1. It's a constant. So somehow we have a jump, right? 0, 0, 0, and 1 here. That means that at this corner and at this corner there is a jump of temperature. That's kind of non-physical, but this is what we have. Can we show what that looks like? Well, E sub n will be twice L sine hyperbolic of lambda n L times the integral from 0 to L of 1 times the sine, so I'm going to write the 1 here, of lambda n y dy. Can we solve analytically the integral of the sine? Yes, that's minus the cosine. Okay, so this is twice L sine hyperbolic of lambda n L times the minus cosine of lambda n y divided by lambda n between 0 and L. Okay? So we have the cosine such that lambda n is equal to n pi over small l. So we have the cosine of n pi. See, when y is equal to L, we end up with the cosine of n pi. What is that? What is the cosine of n pi? The cosine of pi and 0, 360 and 180. What is that? Positive, negative 1, right? That would be to minus 1 to the power of n. When n is odd, you get minus 1. When n is even, you get 1. Same thing. And what is the cosine of 0? So you also need to evaluate y equals 0. What is the cosine of 0? 1. So basically, for this case, when the function on the right hand side is equal to 1, e sub n is equal to twice 1 minus 1 to the power of n divided by n pi times the sine hyperbolic of n pi over L times big L. That's all the constants of integration, the infinite constants of integration in one shot. So then you can go to MathCAD, take this, plug it in here explicitly, make that infinity like 1,000, okay? We can do that in one shot very easily because we have mathematical spreadsheets nowadays. So plug it in there, make that infinity 1,000, and evaluate for all possible values of x and y between, assign a value to L and small l. Let's say that that's a square, 1 by 1 square or something like that, and see what the temperature looks like. You get 0 here, you get 0 there, you get 0 here, and you get a flat function that's 1. Somehow, if that infinite is infinite enough, you approximate a 1, a flat function of 1. And everything in the inside will be a diffusion of that force condition. Everything in the inside will be between 0 and 1. Okay, but in equilibrium with everything. All right. Let's solve another example. Very similar to this one, but slightly different kinds of boundary conditions. Any questions? All right, so we have given. Let's draw the schematics and then we draw the equation of boundary conditions. Again, same geometry in x and y. Internally we have the Laplace of temperature is equal to 0. So this is steady heat conduction with no generation, constant conductivity. That's the equation that governs that phenomenon. 0 to L, 0 to L. And in here we have temperature equal to 0. Same thing we had before. In here we have temperature equal to some f of x. Now not only we're flipping the conditions, now the non-homogeneous condition goes in the y direction, but also we're making this cube equal 0. Now it's a different kind of boundary condition, second kind. Okay, so this is sort of like an insulated boundary. No heat flux can leave or enter through that boundary. We have an insulator. And then here, let's say that we have a flow coming in at h and t infinity. And let's make that t infinity equal to 0 to make it homogeneous. So we have convective condition on the right-hand side because we have some sort of flow with a film coefficient h and a temperature of 0 circulating on the right-hand side. So we have first kind condition, non-homogeneous, second kind, third kind condition, both of these homogeneous, because the value is 0, the value is 0. Okay? So how do we express that? Mathematically, this will be the Laplace of t is equal to 0, that's the second derivative of t with respect to xy, dx squared, plus the second derivative of t with respect to y squared, xy, is equal to 0. And the boundary conditions, let's start with the boundary conditions in the y direction. Those are the easy ones. The temperature at x and y equals 0 is equal to 0. The temperature at x and y equal L is equal to some f of x. Those are first kind and first kind conditions. All right. The condition on the left wall here says that the Q, the normal flux, Qn, at x equals 0, and any value of y along the entire wall is equal to 0. Okay? That means that, remember what a normal derivative is? This is minus k dt d normal. That's how the normal flux is defined. At x equals 0 and y is equal to 0. Now, what is the normal vector on this wall? The normal vector here is minus 1 in the x direction plus 0 in the y direction. So that will be minus k times dt dx times nx plus dt dy times ny is equal to 0. And this is occurring at x equals 0, y. And therefore, since this is minus 1 and this is 0, we have k dt dx at x equals 0, y is equal to 0, and therefore dt dx at 0, y is equal to 0. That is a resulting boundary condition from imposing a heat flux. In this case, a heat flux that is imposed is equal to 0. This is second kind, homogeneous. Remember, the second kind conditions are also called Neumann or natural. And in heat transfer, we refer to them as flux conditions. All right, how about the condition on the right-hand side? That's a convective condition. What do we know about convection? Convection says that the amount of heat flux that goes in is equal to the amount of heat removed by convection, or the amount of heat going out through conduction is equal to the amount of heat going out through convection. So that means the following. The normal amount of heat flux, and again, we have a normal vector on this side, which happens to be positive Ex plus 0 Ey. It's a horizontal normal vector. Qn at x equal L, y is equal to h times t minus t infinity. And that's t at x equal L, y. Alright, so there we go again. Qn is minus k times the t dx and x plus the t dy and y, and that's equal to h times t minus t infinity. And all of these at x equal L, y on both sides. The normal vector x in x is equal to 1, normal vector and y is equal to 0. So what we're left with is, therefore, minus k dt dx. Now c is negative because it doesn't cancel out with an x, the sign, at x equal L, comma y is equal to h times t minus t infinity. And remember that the t infinity that we were given is 0. And this is at x equal L, comma y. And that's simply dt dx at L, comma y. This is minus, so plus h over k, t at L, comma y is equal to 0. And that's how we construct the third kind boundary condition. So this is third kind, and it's homogeneous as well. There's nothing on the right hand side. If t infinity was a number different than 0, then what's on the right hand side makes it non-homogeneous. So that doesn't drive the problem. The only thing that drives the problem are non-homogeneities. In this case, the only thing driving this problem is that condition on the top. Any question? All right. So again, SOV applies because we have a homogeneous governing equation, and we have 3 homogeneous boundary conditions and 1 non-homogeneous one. Okay, so this one is first kind, homogeneous, and this one is first kind, non-homogeneous. So, SOV applies, and therefore we let t of x and y be equal to x of x times y of y. Right? And therefore, the governing equation becomes x double prime of x divided by x of x is equal to minus y double prime of y divided by y of y. And now we need to select the sign equals to plus minus lambda squared. Which sign are we going to pick? Plus or minus? Which one is the homogeneous direction and which one is the non-homogeneous direction? Uh-huh. The what? The x or the y? It's non-homogeneous. Well, minus the what direction? X or y is non-homogeneous. X is homogeneous. Okay, when x is 0 and when x is L, both conditions are homogeneous. In the y direction, we have the non-homogeneity here. You can see it on the sketch better. The y direction is non-homogeneous, so we need to form an eigenvalue problem in the x direction. Okay? It doesn't matter if they're first, second kind, or third kind. They need to be homogeneous. So we are going to pick the minus sign. Select the minus sign because we need an eigenvalue problem in the x direction. By picking that minus sign, what we're going to end up with is x double prime of x plus lambda square x of x is equal to 0, and on the other side we end up with these. Alright, so let's start with the y problem because it's a lot simpler. Y, we have y double prime of y minus lambda square y of y is equal to 0. And so this is, the solution of these is y of y is equal to a cosine hyperbolic of lambda y plus b sine hyperbolic of lambda y. Subject to the temperature at x comma 0 is equal to 0. That means that y of 0 is going to be equal to 0. Okay, we already did that. And therefore, if y of 0 is equal to 0, then a cosine hyperbolic of 0 plus b sine hyperbolic of 0, and this is 1, this is 0, a becomes 0. And therefore, the solution in the y direction is simply b times the sine hyperbolic of lambda y. Where before we had sines in the x direction, sine in the y direction, now we have sine hyperbolic on the y direction. The other condition cannot be used yet, because it cannot be separated. The non-homogeneous condition, remember, is always left until the end to use with orthogonality. Right? Now in the x direction, x double prime of x plus lambda square x of x is equal to 0. That means that x of x is equal to c cosine of lambda x plus d sine of lambda x. Alright, now let's see what we do with boundary conditions. That's where the problem begins. We have those two. We have dt dx at 0 comma y is equal to 0. Alright, that means that d dx of x of 0 times y of y at x equals 0 is equal to 0. That means that x prime of 0 times y of y is equal to 0. And from here, we can conclude that because y of y cannot be 0, then x prime of 0 must be equal to 0. So that's one of the conditions. The other condition says dt dx at L comma y plus h over k, this is a convective condition, at L times t at L comma y is equal to 0. That means that d dx of x times y of y at x equal y, x equal L, plus h over k times x of L y of y is equal to 0. So that means that x prime of L times y of y plus h over k x of L times y of y is equal to 0. And that means that x prime of L plus h over k times x of L times y of y is equal to 0. Right? So y of y is a common factor. And what we're left with is, therefore, x prime of L plus h over k x of L is equal to 0. That's the other boundary condition. And somehow, we are going to use these two boundary conditions here to determine the constant of integration and the eigenvalue, because this is an eigenvalue problem. Eigenvalue problem. So we need to determine the eigenvalues, and remember the eigenvalues are not necessarily n pi over L. That's only true for the case when the eigenfunction is assigned. Alright, so let's use these boundary conditions and see what we get. Well, first of all, the general solution is x of x c cosine d sine. So x prime of x is equal to c lambda negative sine of lambda x plus d lambda cosine of lambda x, right? Such that the first condition said that x prime of 0 was equal to 0, which is equal to minus c lambda sine of 0 plus d lambda cosine of 0. The sine of 0 is 0, the cosine of 0 is 1, and therefore d is equal to 0. Less than 0.
Thank you.
D is equal to 0. So what we're left with is x of x equals c times the cosine of lambda x. This is what we have so far. Alright. We know that applying the other condition is going to lead to the eigenvalues. Let's see. We have the other condition such that x prime of L plus h over k x of L is equal to 0, and that means that x prime is this one here, minus c lambda sine of lambda L plus h over k, the cosine, c times the cosine of lambda L. And we can take c as a common factor. C is equal to times lambda sine of lambda L plus minus hk cosine of lambda L is equal to 0. Again, c cannot be 0, since c cannot be 0, because that will lead to a trivial solution. The only possible explanation for these is that this term right here is equal to 0. Right. So let's let h be equal to h over k, and therefore we have sine divided by cosine. Let's see, put this h on the right hand side, h over lambda. So we have the tangent of lambda L is equal to h over lambda. The roots of these expressions are the eigenvalues lambda n. Let's see how they look like. need to solve for the values of lambda that satisfy these. Okay? So, if we plot this, lambda, how does the tangent of lambda L look like? So we have I over 2L. We have pi over 2L. We have 5 pi over 2L. And 7 pi over 2L. The tangent of 0 is equal to 0. And the tangent of pi over 2 is infinity, right? So this one goes like this. This is what the tangent looks like. So this is the tangent of lambda L. Well, that axis should have been closer here. This is half the axis. All right? And what does the function h over lambda on the right-hand side look like? When lambda is equal to 0, it's infinity. When lambda is equal to infinity, it's equal to 0. So the function h over lambda is an asymptote that looks like this. So these are all tangent of lambda L. This is tangent of lambda L. Tangent of lambda L. And here, 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 and here, this will be when the two actually are equal to each other. This is a root 1, root 2, root 3, root 4. There's an infinite number of values of lambda that make this equation on the left equal to the equation on the right, but it's not explicit. They are not equidistant from each other. They're periodic. Sorry. There's an infinite number of them, but they're not periodic because they're not equidistant from each other. So eigenvalues are simply expressed. Values are expressed implicitly as the roots of the function tangent of lambda n L is equal to h over lambda n. And the eigenfunctions are x of x is equal to the constant of integration. We have found d is equal to 0, so it's c times the cosine of lambda n x. There it is. So, let's put it all together before we leave. Thus, therefore, the general solution t of x and y is equal to x of x times y of y is the summation from n equal 1 to infinity of e sub n cosine of lambda n x times the sine hyperbolic of lambda n y such that the eigenvalues are determined by these. and ENs are determined by using the remaining non-homogeneous BC that says that T of X and L is equal to F of X right? And that's it. So next class, we'll continue with this problem, finish it up real quick, and go to a 3D problem. And then we'll try to do some numerical simulation. We'll do the transient ones and then numerical simulation. Okay? So I'll see you Tuesday.
Anyways, that was so very helpful.